Let's start with a simple question. It is a big one. What if we could change our sun? Imagine waking up one morning to a different star in the sky. Our sun is the center of our solar system. It gives us light. It gives us warmth. It gives us the energy for life to exist on Earth. Everything we know revolves around it, quite literally. This giant, glowing ball of hot gas. It is familiar and constant, but the universe is filled with countless other stars. They come in many different sizes. They come in many different colors. They come in many different ages. This thought experiment is a cosmic what-if that lets us explore those other stars. It helps us understand our own place in the cosmos by imagining a different reality. By swapping our sun, we can see how special it truly is. This is not just a fantasy. It is a way to learn about astrophysics in a very personal way. We will take a journey through the galaxy without ever leaving home. We will see what would happen to our planet. We will see what would happen to our days. We will see what would happen to our lives. If a different kind of star took the sun's place, would Earth freeze? Would it burn? Would it be thrown into a new, strange orbit? Each swap tells a different story about the laws of physics. It reveals the delicate balance that makes life on Earth possible. It shows us just how dependent we are on our star's steady nature. This experiment is like being a cosmic architect. We get to build new solar systems and see what happens. We will place a new star exactly where our sun is now. Then we will watch the consequences unfold. This is a safe way to explore dangerous and powerful cosmic events. We can witness the fury of a giant star, or the quiet chill of a dying one. We can ask questions about gravity. We can ask questions about light. We can ask questions about heat. This journey will challenge our ideas about what is normal. It will make us appreciate the yellow dwarf star we call the Sun, which has provided a stable home for billions of years, allowing life to take root and flourish. Thinking about these cosmic swaps is more than just an exercise in imagination. It connects us to the grand scale of the universe. It helps us understand the life cycles of stars, from their fiery births, to their quiet deaths, to their explosive deaths. By looking at these alternatives, we gain a deeper appreciation for our own solar system's history and its future. We learn why astronomers search for planets around stars that are similar to our own sun. The stability of our star is the bedrock of our existence, and by imagining its absence, we can truly begin to understand its profound importance to every living thing on our world. In this cosmic exploration, we will conduct 5 different swaps. Each swap replaces our sun with a different star. We begin with a red dwarf, most common stars in the universe, much smaller and cooler than our sun. Imagine a dim, red sky. Next, a red giant, old bloated stars near the end of life. A star swells to enormous size, threatening to swallow inner planets. A glimpse of our sun's distant future. After that, a white dwarf. The small, dense core left after a sun-like star dies, hot at first, but with no fuel to burn. A dying ember in the dark. How would Earth fare next to one? Then we turn the power up. A blue supergiant. Cosmic titan, massive and blindingly bright. They burn fast and end in spectacular explosions. Such a swap would upend the solar system. Finally, the most extreme swap. A compact object, a neutron star, a black hole, tiny, mysterious with immense gravity. They warp space and time. Placing one at the center would unleash incomprehensible forces. This shows the true power of gravity in extreme cosmic conditions. A journey to the edge of physics. For each swap will explain exactly what happens. Simple terms and clear comparisons. Immediate effects on Earth. Light in our sky, heat on our skin. Long-term changes. Orbit climate, the future of life. Get ready to see our home in a new light. This journey will bring wonder, surprises, and a new respect for our sun. Let our cosmic experiment begin. Imagine you wake up tomorrow and something is wrong. The morning light filtering through your window is not the familiar bright yellow it has always been. Instead, the world is bathed in a dim, reddish glow, like a permanent sunset. You look up, and where our brilliant sun should be, there is a new star. It is a small, cherry red orb, hanging in a sky that seems darker than usual, even at midday. This is a red dwarf. We have just swapped our sun for the most common type of star in our galaxy. It is much smaller, cooler, and dimmer than the star we are used to. The change would be immediate and profound, altering the very color of our world. Our new red dwarf sun might have the same mass as our original sun to keep our orbit stable, but that is where the similarities end. Red dwarfs are famous for being faint. The light reaching Earth would be a tiny fraction of what we receive now. Even the brightest red dwarf would make our daytime look like a deeply overcast evening. The sky would no longer be a vibrant blue. A blue sky is created when our atmosphere scatters the sun's powerful blue light. With so little blue light coming from our new star, the sky would likely appear a dark, bruised purple or even black, with stars visible during the day. The quality of this new light would also be completely different. Our sun provides a broad spectrum of light, which is what plants use for photosynthesis. A red dwarf, however, emits most of its energy in the red part of the spectrum. A red dwarf emits most energy in the infrared part of the spectrum. This is light that we feel as heat more than we see as brightness. For human eyes, the world would be shrouded in perpetual twilight. Colors would look strange and muted. Reds, grays, blacks. It would be a somber, silent-looking world, forever stuck in the last moments of dusk. This sudden plunge into dimness would be a shock to every living thing on the planet. Our circadian rhythms, the internal clocks that tell us when to sleep and when to wake, are tuned to the sun's 24-hour cycle of bright light and darkness. With a dim red star, that clear signal would be gone. Confusion would reign in the animal kingdom. Birds might not know when to sing, and nocturnal animals might not know when to hunt. For humanity, it would feel like the world's light switch had been turned down to its lowest setting, permanently. The psychological effect of losing the bright, cheerful daylight we know would be immense. The dim light from our new red dwarf star is just the beginning of our problems. The bigger issue is the lack of heat. Our sun bathes Earth in energy, keeping global temperatures comfortable. A red dwarf, much cooler on its surface, would send us far less warmth. The moment the swap happens, Earth would start to lose heat to space far faster than it gains it. The effect is like throwing open all the windows in a blizzard. The planet would immediately begin to cool down, catastrophic and swift. Within just a few weeks, the consequences would be obvious. The average global temperature would plummet far below freezing. First, the polar ice caps would expand rapidly, creeping down from the Arctic. Then, ice would creep up from Antarctica. Next, the oceans would begin to freeze over, starting at the surface. A thick layer of ice would spread toward the equator, reflecting what little heat remains. That reflection would speed the cooling, a runaway feedback. This ice albedo feedback would lock our planet into a global ice age. The atmosphere would change dramatically. Water vapor in clouds would freeze and fall as snow, never to melt. Soon, other gases would follow. Carbon dioxide would freeze into dry ice snow. It would fall and coat the surface in CO2 frost, lose the greenhouse gases, lose any ability to hold warmth. Earth would become a snowball, hurtling through space with a thin, frigid atmosphere. For surface life, this deep freeze means extinction. Plants would die within days, unable to photosynthesize. Animals that depend on those plants would soon follow. The oceans, once teeming, would be entombed in ice. The planet's surface would become a silent, white desert. Temperatures would stabilize around -100 degrees Celsius, -150 degrees Fahrenheit, or colder. Earth becomes a barren ice world, its history frozen under miles of ice for eternity. As if a global freeze was not enough, our new red dwarf sun would introduce another strange phenomenon: tidal locking. Just as the moon is tidally locked to Earth, Earth would eventually become tidally locked to its new star. The star's gravity pulls on the planet, creating a slight bulge. Over millions of years, the tug slows the planet's rotation, until one side permanently faces the star. Our 24-hour day-night cycle would disappear, one hemisphere trapped in endless dim daylight. the other frozen in perpetual night. The side facing the red dwarf is the day side. Constant light, but not warm. Even with continuous exposure, the day side remains far below freezing. Still, it would be warmer than the night side. The night side would never see the sun again. An abyss of absolute cold, cold enough to freeze nitrogen out of the atmosphere. A vast permanent ice cap would cover the dark half. Between them, a thin strip, the Terminator Zone, the Twilight Zone, a band of permanent dawn or dusk circling the planet. Here, the red dwarf would hang forever on the horizon. This zone might be the only possibility for any kind of stability. Temperatures could be slightly less extreme here. Some frozen gases from the night side could melt, creating a thin, weak atmosphere, driven by winds blowing from the slightly warmer day side. This new planetary reality would create weather patterns unlike anything we have ever seen. Giant, permanent storms might rage at the point directly under the star. Powerful winds constantly blow from the hot spot on the day side to the cold spot on the night side. The thin atmosphere tries to balance the extreme temperatures. Day side, a frozen desert under a dim red sun. Night side, an even colder wasteland of frozen air. The Twilight Zone would be a place of eternal twilight, battered by relentless winds, a thin ribbon of dim hope on a dying world. With the surface of Earth transformed into a frozen, airless wasteland, is it possible for any life to survive? The answer is a faint maybe, but not in any form we would recognize. Complex life, plants, animals, humans, would be gone. Our survival depends entirely on the stable, warm and bright conditions our sun provides. But simple, single-celled life is much tougher. On Earth today we find extremophiles, organisms that thrive in the most hostile environments imaginable. They live deep underground, in boiling hot springs, at the bottom of the ocean, far from the light of the sun. These are the kinds of life that might stand a chance. The best hope for survival would be deep beneath the ice, in the planet's oceans. The surface of the oceans would be frozen solid, but immense pressure from the ice and heat from Earth's core could keep water liquid at the very bottom. Here, around hydrothermal vents, life could continue. These vents are cracks in the ocean floor that spew out hot, mineral-rich water from the planet's interior. On our world, these vents support entire ecosystems that have never seen sunlight. They get their energy not from the sun but from chemical reactions. This is called chemosynthesis. It could be the key to survival. These deep-sea oases would be isolated pockets of life in an otherwise dead world. Cut off from the surface by miles of ice, they would be unaware of the star swap. Life in these refuges would evolve in total darkness and crushing pressure for billions of years. The creatures there would be strange, adapted to chemical energy and eternal night. The surface would remain a silent memorial to the world that was, while a secret biosphere persisted in the deep. One of the most remarkable things about red dwarf stars is their lifespan. While our sun will burn for about 10 billion years in total, a small red dwarf can live for trillions of years. They sip their hydrogen fuel incredibly slowly, like a car that gets 1,000,000 miles to the gallon. By swapping our sun for a red dwarf, we've traded our star's brilliant but finite life for an almost unimaginable future of length. Earth's fate becomes long, defined by stable cold and near darkness. Our planet would be locked in a billion-year winter. If life survived, it would have enormous time to evolve. On our current Earth, complex life took about 4 billion years to appear. With a red dwarf, the clock resets and the timeline stretches almost infinitely. But red dwarfs have a violent youth. Many are flare stars when young. They can erupt with powerful flares, emitting X-rays and charged particles. A flaring red dwarf could periodically strip away any fragile atmosphere. Those flares would be deadly for surface life, especially around the Terminator Zone. So life would likely be confined to deep, shielded refuges for a very long time, waiting for the star to calm, which could take billions of years. The red dwarf swap is a story of loss and endurance. We lose the world we know, the vibrant, dynamic planet we love, and replace it with a frozen, silent globe. We lose the sun's warmth and light, but we gain time. It is a lonely, cold future, but one that lasts a very, very long time. A quiet testament to life's persistence in unlikely places. Let us perform our next swap. This time, we are not downsizing. We are going big. We will replace our sun with a red giant. A red giant is what a star like our sun becomes when it gets old. After billions of years of burning hydrogen, it starts to run out of fuel in its core. The core collapses and gets hotter. It ignites hydrogen in a shell around the core. The outer layers swell up like a giant fiery balloon. If we swapped our sun with a red giant of the same mass, our orbit would remain the same. But the star itself would be terrifyingly close. The new star in our sky would be horrifying and magnificent, not a point of light. It would fill the sky, horizon to horizon. The light would be intense. The heat would be the real killer. Earth would be like a moth that flew into a furnace. The change would be instant. The consequences final. 2 possible fates depending on the red giant's size. Many red giants would swallow the inner planets. Mercury, Venus, Earth might be next. If our orbit fell inside the star's new boundary, Earth would be vaporized. Oceans, mountains, history merged into the star's mass. A swift, total annihilation, a silent plunge into stellar fire. Even if we're not swallowed, it's no better. We'd be orbiting perilously close to the scorching surface. The star would be a colossal wall of fire in our sky, heat thousands of times greater than today's sun. The facing side of Earth superheated to thousands of degrees. A world-ending inferno, no room for survival. Not a slow decline, a sudden, violent end by a dying star. Let's imagine our planet is lucky enough to avoid being swallowed. The immediate effect would be the boiling of our oceans. The sheer energy hitting the planet would flash boil the water, sending colossal clouds of steam into the atmosphere. This would create a runaway greenhouse effect, trapping even more heat. The surface temperature would skyrocket, far hotter than the inside of a pizza oven. The ground itself would begin to melt. Rocks would turn to liquid. The continents would dissolve into glowing rivers and seas of molten lava. The entire surface of Earth would become a roiling magma ocean. Any trace of our civilization, our cities, our monuments, our farms, would be erased in minutes, sinking into the molten rock. The atmosphere would be stripped away by the intense stellar wind. Our protective shield of air would be sandblasted into space, leaving the molten surface exposed. Earth would become a glowing ball of liquid rock. From space, Earth would be unrecognizable. No longer a blue and white marble, it would be a featureless, bright orange orb, glowing with its own intense heat. But red giants are temporary. After a few million years, the red giant sheds its outer layers. At the center, a tiny, super-dense core remains. Our scorched, molten Earth would then orbit this stellar remnant, a silent, charred cinder, a testament to the destructive power of a dying star. It is a dramatic and violent end to our world story. Now, for our third swap. We have seen the fiery end of a red giant. What about what it leaves behind? We will now replace our sun with a white dwarf. A white dwarf is the dead core of a star like our sun. After the red giant phase, the outer layers drift away. All that is left is a small, incredibly dense object about the size of Earth. It has no nuclear fusion left to power it. It is essentially a stellar ember, glowing with leftover heat. We swap our sun for a brand new, scorching hot white dwarf. The first thing we'd notice is the light. A new white dwarf is extremely hot. It would shine with a brilliant blue-white light, yet it is incredibly tiny. The new star would be a dazzling pinpoint of light, like a diamond against the blackness of space. The total light and heat reaching Earth would be far, far less than from our sun. This sudden drop would trigger a deep freeze. The planet would become a snowball once again, but the quality of the light would be different. A white dwarf's light is rich in high-energy ultraviolet. The sky might have a strange violet hue, a cold, sterile light offering no warmth. The most striking feature would be the visual contrast. Our solar system transformed into a cosmic snow globe, a tiny perfect star at its heart, planets frozen in ice and silence. A white dwarf has no internal fuel source. It is constantly cooling down. From the moment the swap happens, our new star would begin to fade, turning yellow, then orange, and finally a dull red over countless millennia. The planet, already a snowball, would get even colder. The last vestiges of the atmosphere would freeze solid, coating the surface in a layer of nitrogen ice, oxygen ice. Earth would become an inert ball of rock and ice, indistinguishable from any other lifeless body in the outer solar system. Eventually, the white dwarf would cool so much that it no longer emits any significant light or heat. It would become a black dwarf, a cold, dead lump of superdense matter, invisible in the darkness of space. Earth would continue to orbit this dark object, a frozen tomb in a dead solar system. This is perhaps the most complete and final end, not a fiery destruction, but a slow, cold fade into nothingness, an everlasting night from which there is no dawn. Let us perform our most dramatic swap yet. Replace our sun with a blue supergiant. These are the rock stars of the cosmos. They are incredibly massive, some with dozens of times the mass of our sun. They burn with a fierce blue-white intensity, among the brightest and hottest stars. Place one at the center of our solar system. Instant and terrifying, the sky would ignite, replaced by a blazing, brilliant orb. Painfully bright to look at, overwhelming our senses. The star's mass would wreak havoc. Its gravity would be much, much stronger. Orbits of all the planets would change immediately. Earth yanked into a faster, tighter orbit. Our year shortened, from 365 days to perhaps only weeks or months, like replacing the calm center of a carousel with a roaring jet engine. The ride becomes violent, chaotic, short-lived. A blue supergiant is a tyrant star. The immense energy from the blue supergiant would deliver a death blow. The star's light is incredibly rich in high-energy ultraviolet and X-ray radiation. The ozone layer would be obliterated in seconds. The heat would be just as devastating. The oceans would not just boil, they would be flash vaporized. The atmosphere itself would be superheated and energized, causing it to expand outwards. This would effectively sandblast our atmosphere away. Our planet would be stripped bare, layer by layer. First, the life, then the oceans, then the atmosphere. Soon, the surface itself would begin to melt. Earth would be transformed into a barren, airless ball of magma, a scorched, sterile rock orbiting a cosmic furnace. Even the outer planets would not be safe. The entire solar system would be fundamentally and permanently altered. It remakes its entire stellar system in its own fiery image. It is a comprehensive, system-wide apocalypse. The most terrifying thing about a blue supergiant is not just its life, but its death. These stars live fast and die young. A blue supergiant burns through its fuel in only a few million years. By swapping in a blue supergiant, we've started a cosmic time bomb with our planet sitting next to it. When the supernova happens, the star will briefly outshine the entire galaxy. A blast wave of energy and matter would erupt outward at nearly light speed. Being so close, Earth would be hit head-on. The planet would be bathed in a flood of gamma rays, so intense it would vaporize solid rock. There would be nothing left. Earth would be instantly and completely annihilated, its atoms scattered across space, to become raw material for future stars and future planets. A supernova is both destruction and creation. The explosion forges heavy elements, gold, uranium. The iron in our blood formed in a massive star that exploded billions of years ago. So the planet's destruction is also cosmic recycling. The atoms that made our mountains, our oceans, and our bodies would be cast into the interstellar medium to form a new planet where life can begin again. We are made of stardust, and in this scenario, our world returns to stardust. For our final and most extreme swap, we will use a compact object, a stellar mass black hole. Let's choose a black hole with the same mass as our sun. The moment the swap happens, all light and heat from the sun would vanish. Earth would be plunged into a darkness more profound than any night. This would immediately trigger a deep freeze. With zero energy input, the planet's temperature would plummet towards absolute zero. The oceans would freeze solid in a matter of days. The atmosphere would collapse and fall as snow. A black hole warps the fabric of space-time. We would be able to, see it by the way it bends the light from the stars behind it. The stars near the black hole in our sky would appear distorted and warped. If any matter, an asteroid, a comet, were to stray too close, it would be torn apart and form a swirling, superheated accretion disk. This disk would blaze with high-energy X-rays, blasting the solar system with deadly radiation. The solar system would become a gravitational pinball machine. Planetary orbits could cross, leading to catastrophic collisions. Or worse, it could be ejected from the solar system entirely, as a rogue planet. Another terrifying possibility is that its orbit could decay, causing it to spiral slowly inward towards the black hole itself. As Earth got closer, the black hole's immense tidal forces would begin to stretch the planet. Spaghettification. In its final moments, our planet would light up the dead solar system, screaming with high-energy radiation before disappearing forever across the event horizon. The very atoms that made up our world would be torn asunder and consumed by the singularity. Our cosmic journey is now complete. We have seen our world burn, freeze, and be torn apart. Our journey brings us back home with a new perspective on the star we see every day. It is, in many ways, a Goldilocks star. Not too hot, not too cold. It is just right. Our sun, a humble yellow dwarf, balances light and energy to support a complex biosphere. Its energy output has been remarkably stable for billions of years. That stability is the true miracle. Our fate is tied to the life cycle of our star. In about 5 billion years, our sun will run out of hydrogen fuel. It will begin to swell, becoming a red giant. Its fiery surface will scorch the Earth. So, what does this cosmic thought experiment truly teach us? It teaches us about humility, appreciation. Our existence on this small blue planet is the result of a long chain of fortunate circumstances. We are here because we orbit the right kind of star, at the right distance, at the right time in its life. The gentle, steady nature of our yellow dwarf has allowed us to flourish. As we look up at the night sky, filled with countless stars of every kind, we are left to wonder, are we alone? Or has another world found its Goldilocks star? The search for that answer is one of humanity's greatest adventures, a journey that continues every time we look up and wonder about our place in the cosmos.